Hi, in this video, we want to take a look at detecting outliers in multivariate data using clustering. Okay, so think of the situation where we have multivariate data with a lot of columns, and we're talking specifically about numeric data. Well, it can be difficult to detect outliers and anomalies. So what we want to do in this video, we want to look at using clustering, specifically single linkage clustering, to find outliers. So here's the big idea of this. If I do clustering and observation is by itself in its own cluster, then it's possibly an outlier or an anomaly in our data. It might be an error, right? All right, so basically what we're going to do clustering. If we see like a clustering of maybe just a few data points, or a cluster that has just one observation in it, then we suspect that it is an outlier, and we'll go ahead and look more closely at it. And what can we do with outliers? First and foremost, we can just leave it alone, leave it in our data, and run everything as is. Now, that's not to say we don't know about it. Detecting a possibly problematic data point and knowing about it is better than running forward without knowing about it, right? We can omit the observation. Also, we could impute the values of it to pull it more, pull it so that it's more similar to the other data points. All right, so let's go ahead and run an example. So here we're going to work with the C Horizon data set from MV outlier. And I'm just putting digits down to 2 just so we get less output in the document, make it a little bit easier. All right, so when we're doing clustering, I don't want every single variable I have because ID variables are not pertinent to this. Also, in this data set, they have X coordinates and Y coordinates. And coordinates, I doubt I should keep for the nature of this data. It's a bunch of like scientific measurements, and scientific measurements and geographic locations, I don't think that these are appropriate to include in the same data set. So I'm going to go ahead and filter out the ID variables and the coordinates. Also, inspecting the data set, I noticed that some of the columns were constants. They always had the same value. And well, that's an uninformative column. I want to kick it out. So what I did to identify the ones that are constant, I used standard deviation. So if we have a standard deviation of 0, we know that it is a constant column. Every value is equal to the mean. Therefore, it's uninformative, not useful. So I'll kick it out. So here what we're doing is we're saying that I only want the columns that have column standard deviation greater than 0, and the column is not an ID variable nor a coordinate. Here's the X coordinate and the Y coordinate. Now, furthermore, when we do clustering, most of the time we want to rescale our data. Now, if I don't do that, in general, the columns that have greater standard deviation will have greater influence on the cluster model, and just because of the magnitude. Now, if they're all relatively close in magnitude, or they all have like a same capped minimum and maximum range, I might just leave it alone. But most of the time, I'm going to rescale. If you don't know, rescale. So here, we're subtracting the mean off of each column and dividing each column by the standard deviation after the subtraction. So now, when we do hierarchical clustering, there are 2 choices we need to make. First choice is the distance metric. Second choice is the method of determining clusters. All right, so first thing we're going to do, we're going to come up with a distance matrix. So I have to choose a distance metric. R gives us several options: maximum, Manhattan, Minkowski's, Euclidean, Canberra, and binary are the ones that come out of the box with the stats package for the dist function. Now, what's going to happen as I run this, I'm going to get a distance matrix. So the distance matrix is going to measure the distance between any 2 observations after I've rescaled them. And then I'm going to take that distance matrix, I'm going to put that into the clustering algorithm, and that's how I'll actually get my clusters. Now, something I'm doing here is I'm using the lapply function to relatively quickly get all of the distance matrices quickly. Now, why am I doing it this way? Well, as I work through this problem, I may or may not want a certain clustering, and I want to take a look and see which one's the best. Now, if I have a large data set and it's not reasonable to slug through all of this, honestly, I would just use the Euclidean distance or the Manhattan distance, depending on my problem. Probably maximum would be also another good choice. I'll just grab one, run with it, and go for it. If I have big data, usually I would use Euclidean in that case, but the other ones are useful. But in smaller data cases, I'll go ahead and compute distance matrices on all of them. And that way I can pick the clustering that I feel like is the most applicable to my problem. Now, after I have all my distance matrices, so here, this is the output, list underscore dist is the output. And this is the vector of the method, the metric for distance evaluation. And I'm passing my prepped data set into the dist function along with the individual metric name. And that's going to give me the output of the matrix I want. Once I have that, I can run hierarchical clustering on each one of these. So now I'll notice I have a bunch of different methods for determining which observations go together inside the clusters. In general, most of the time, the step that will take the longest is going to be computing the distance matrices. So if I have a big data problem, what I could do is run maybe just one distance matrix and then run several hierarchical clustering so I can explore different ways to cluster. That way I'm not spending a lot of time. If I run through all of these with big data, it's going to take too long. Now, when it comes to the method of actual clustering, I find that Ward D is a good choice if I want relatively even number of observations in a cluster, and single linkage is better for detecting outliers. That's my personal experience. You can check it out, explore it. I haven't seen that actually written down, but this makes sense because Ward D works to minimize the standard deviation within a cluster, and single linkage looks at individual observations and tries to find the individual connecting to another cluster. And so I kind of see the hierarchical methods as being on a spectrum. And this is roughly the order that I see them in. Now you'll notice that if you look through the internet, complete linkage is by far the most popular. Complete linkage is very good for a lot of things. It leans more to the Ward D side, in my opinion. Complete linkage has a nice interpretation, but when I'm working on a machine learning problem, I really don't care about interpretation. I worry about good, solid clusters. And because of that, I really don't worry about the interpretation at all. But you'll see over and over and over, if you look through different help documentation, complete linkage is the more popular one. All right, so now what I'm going to do is I'm going to take the hclust function. I'm going to pass my distance matrix into it, and I'm going to run a particular method. And what this is going to do, since I'm using the lapply function, you'll notice I have a nested lapply. So I'm running lapply inside to get the clustering, and then I'm running lapply around the inner one. And this is passing the distance matrix, and this is passing the method of clustering to the hclust function. Rather slick code right here. And this is probably the fastest way to implement this in base R. Remember that in R, for loops are slow. For loops probably would have been a little bit easier to interpret, but I went ahead and went with this way. Something I do on projects is I will convert heights to the ranks within each clustering. That I do this so that the dendrograms have a more even presentation. It's easier to compare, but I decided not to do that for this video. So I just commented it out. But if you want to do that, go for it. There's the code. get rid of the comments. All right, so now what I want to do, I want to plot all these individual dendrograms. So by plotting these, I want you to take a look and see what is the overall shape of each of these. All right, so if I look here, all right, so maximum got cut off the top, but I can see going down. So we have maximum, distance, and single linkage, and all of these are single linkage. All of these are maximum distance. All of these are wards D linkage, and all of these are Canberra distance. All right, so if I look here under single linkage, I can see this kind of shape that what it's doing is like it's pulling out one observation to be in, or one or a few observations to be in a cluster by itself. Then as I go down, it pulls off from the big one, it pulls off another individual or small number, then pulls a little bit lower, it pulls off an individual or a low or just a few, and it keeps on doing this all the way down. Let's contrast this with, let's say, what's a good one to look at? Look at Minkowski's ward D2. So this one is working to minimize the variance and it's using Minkowski's distance. Do you see that if I cut up here, roughly speaking, roughly, I have about equal number of observations in each cluster. And you'll notice if you look from left to right, overall, it's a much more even distribution of observations on these as I look through. So if I go through and look at these, like here, you know, now it's not exactly 50-50 on the two split, but you know, you can look and you can see that, you know, on the ward D side, the size of the clusters are much more even. Complete linkage is somewhere in between ward D and single linkage for this. And then each distance matrix gives something a little bit different for all these as I work across, as I look down the line. All right, so something I like to do, I like to look at the agglomerative coefficient from the cluster package to kind of see what's going on, get an idea of what's up. And so what this code is doing is I create a matrix that stores the coefficient, and then I go through and for each row and each column, I take the distance matrix method and I take the single linkage, sorry, not single, the clustering method, and then I compute the coefficient of agglomeration for each one, and I pass it into the matrix. And if I look at the matrix, here's what we get. So we can see that the clustering with the lowest agglomerative coefficient was Canberra distance with single linkage. And then we can see that ward D had the largest, you know, was it every single time. And we can kind of see how things compare throughout. So if I look through, I can see Canberra has substantially lower than a lot of the other measurements. And we can see that single linkage had lower than the other ones, not as much as Canberra's difference. So what I choose to do based off this information, I'm going to go with I'm going to go ahead and explore the Manhattan distance with ward D right here, because that's relatively large. And I'm going to look at Canberra distance with single linkage because that's very small. I'm grabbing the most extreme ones. And I want to find a cluster model that fits my purpose. It's going to be single linkage, but just for now, pretend I didn't know that. My experience is that the greater the agglomerative coefficient, the more suited that is for even groups, while single linkage or with the smaller coefficient is usually better for detecting outliers. All right, so here is with Manhattan distance and wards D. And so here it's, you know, I really don't see anything as being an outlier for this purpose. So now this is a good clustering. This would be useful, because I can see that my cluster sizes will be relatively similar size, which is good. Now let's look at Canberra distance with single linkage. And I can see that over here, there's a single point getting pulled off by itself. I go down here a little bit and there's a net. I looked at this before making the video more closely because of just the presentation and the number of observations. It's hard to see, but very consistently, 1, 2, or 3 observations are getting pulled off as I go down. So one gets pulled off, then I have the rest of the group. One gets pulled off, then I have the rest of the group. One gets pulled off, I have the rest of the group, and it keeps on doing this pattern, for quite a bit. And when, points get pulled off, it's usually not a very big group. This is very consistent with single linkage. All right, so now let's go ahead and take a look at what are the sizes of our clusters. All right, I am in a room that has an automatic light. Hey, that was not anticipated by me. I'll be right back. There we go. All right, so I've got a table, and so here I went ahead and sorted the label of the cluster. So remember, when we're talking about hierarchical clustering in R, they get labeled as 1, 2, 3, 4, 5, and so on. So what I did, because the labels are really meaningless for our purpose, I went ahead and sorted just so I can see like real quickly what the sizes are. So the smallest group is cluster 11 with only 4. So that's not as many as I expected. And the largest is 1 with 134. Okay. Now, if I look at the single linkage one, we can see that we have what, 10 clusters with only 1 observation. All right, so if I'm worried about outliers, I'm worried about those 10 because these are each floating around by themselves in terms of single linkage clustering. And we can see that all other observations are in 1 cluster. All right, so and how I got that, I used the Q tree. I think it's supposed to be cut tree, but missing a T. And I set it to 11. So I explored different possibilities before making the video. I picked 11. All right, so to take a look at my clustering, what I'm going to do, I'm going to plot the first 2 principal components, and then I'm going to color my points by their cluster. And here we can see when I look at the Manhattan and Ward's D, these are like relatively even-sized groups, approximately speaking. Now here we can see the 4 that are off by themselves. Now remember that this is like, this is a much bigger data set, that there are a lot more dimensions to this data, and I'm compressing it down to 2. So my clusters being on top of each other is okay because, there's maybe like 100 variables or something in this data set. And so if there's 100 columns, I'm taking 100 dimension space and compressing it down to 2 with a projection. And so there's going to be a lot of information lost here. And so it's okay for them to be stacking because, I mean, potentially you could imagine those points coming out of the screen and then floating, like here's the gray, here's the blue, here's the yellow, here's the green, and so on, in kind of like layers. And it'd be far more complicated in higher dimension. Now, if I look at single linkage, we can see that the big group is in red, but I have individual points kind of floating around by themselves. And these are the points that we're interested in as outliers. So what I would do if I was working on a project and I was worried about outliers and anomalies, I would look at each of these individual points, I would pull them out and explore what's going on. Maybe there's an error, maybe there's a mistake, maybe the sensor broke on that observation, maybe a different employee was working on data recording on that day, and so we had weird numbers coming out. We don't know. All right, so now I want to show why this is a good method to consider, at least compared to the univariate method. So if I'm dealing with univariate outlier detection, what I'm going to do is I'm basically going to look for extreme values. If I normalize, maybe like outside of -3 to 3, so normalize, I subtract the mean, divide by standard deviation, and there I'll be looking for observations that after the rescale, either the value is greater than 3 or less than -3, because on the normal bell curve, that's pretty far out. Okay, well, if I look here, if I look at the range of values from the detected outliers, here is the actual column minimum and maximum for each of these. And I sorted it by the average, but you can see that, all right, negative 2.5, I might not pick up on that for an outlier. Let's see, if I look through these, most of these, if I'm using the univariate method, I will not detect as being outliers. And when I'm considering just one variable at a time, that looks very reasonable. But when I consider all variables at the same time, all of these are out from everybody else. If I look back up here, you can see that this point is off by itself. It's completely away from everybody else. And if I'm worried about outliers, I need to inspect that individual value. Let's see, where's one that we would absolutely take a look at? One of these has like a 7 in there. Oh, here we go. So if I look here, I know if I was looking for outliers, this column and this column in the univariate methods, I would be like, hey, there's something to investigate, something to take a look at off of these. The rest I would completely miss. Well, that's all I've got for you. Take care and goodbye.